but I think it's really important, and we're really lucky to have him. Jacob is the CEO of a company called Minds Mechanical. He has a long background in aerospace. He'll talk a little about that, and really has been, from what I can tell, almost sort of reared on around the 787 aircraft, which was really the first composite aircraft, and sort of knows the ins and outs of that like nobody else. And so he can tell us some good stories and give us some good insights. So thank you, Jacob.
Well, thank you to Autodesk for this opportunity, and thank you for not snoring through my presentation. It is going to be the driest presentation you see, but it's also probably one of the most important things for aerospace as well as satellite technologies. I like to say I work on basically anything that flies, drives, or goes boom. So it's basically all the advanced technologies where you're looking at extreme tolerances. So what is measuring quality? Well, it's something that's now required, but not really desired by many. It takes a lot of time, and people don't like it. You have CMMs, traditional CMMs. They're looked and viewed as bottlenecks within a system, rather than what they should be as a helper to your byproduct going forward, and we'll get into that more. So we've had a lot of talk about 2 millimeters, 1 millimeter. These are some of the tolerances I like to work in. 8 microns is the size of a red blood cell. You have 2 microns, which is a bacteria. The smallest I've ever had to measure was 258 angstroms. Now, an angstrom is the size of an atom. So we're talking extreme tolerances and trying to figure out solutions to be able to do this, because a lot of times there is no solution. You have to make it. So moving forward, first of all, we have blueprint product creation. That's our standard still today, actually. Models are coming, they're getting there, but over 60% of our customers and companies all still work off blueprints for measurement. And that is the standard today. Mainly because FAA dictates us holding information for 40 years. And so far, nothing we have can actually hold information for 40 years other than paper. So that's still the standard. Moving forward, we have model product creation. It's coming, it's going further, getting faster, and we can have teams in Asia, Europe, as well as the United States, all working on the same product together and actually create an airplane from it if we wanted to, and all in real time. Using model-based definition, GD&T, it allows us and ensures us to be able to measure everything very accurately along the lines of being able to take all the information and know we got it. If you noticed on the blueprint, it's pretty chaotic if you want all your information. So going through it, it's a tedious process. You have to measure everything very slowly and make sure you get it all. So easy to make sure, no need for blueprint at this point in time because, you know what, just measure to the model. You can align it. There's great softwares out there now. Align it, measure it, report it. And there's a third, little less known, is the reverse product creation. A lot of our products nowadays, like our helicopters, our planes, I mean, the A380 and the 787 are the 2 first aircraft for jumbo jets to ever be fully modeled. Most of our aircraft still are blueprints. I like to tell a story about I reverse engineered the 747-4, and when I went to lock into the golden points, I needed some of the blueprints, and golden points are what aligns us to an aircraft. They pulled out a dusty old box with a lock on it for me. Broke it out, we put out all these blueprints, and unfortunately a golden point had changed, and an engineer redlined it, put his name, as well as his phone number, and unfortunately the guy had been dead for 20 years. So models and blueprints, they're not going away, but we can reverse engineer things and create something kind of like this. Stage 1 of the reverse engineering process, measuring. Either station lines, waterline, or full coverage. Doesn't matter, whatever gets you the best accuracy that you're looking for. Second stage is creating a either quadratic or polygonized mesh. Third stage is creating the CAD from that. And then the fourth stage, the little known fact, is actually making sure what you create is correct. That's probably the most important stage because every CAD software has a little bit different algorithms. One of the big problems we have in the industry is that reason. When we create CAD, throw it into another CAD software, we get something else. But this is actually a Apache rotor blade. Pilots went out, tested multiple helicopters, found the helicopter they liked the best, along the lines of jitter, shaking, and then created a new blade from that for these helicopters since they were all done on old molds. So we created a brand new mold from that, created brand new rotor blades, and went forward. So this is another one. A lot of things are moving towards composites. Composites are becoming our standard for aircraft now, especially military as well as commercial, getting more and more. As you can see, this is a inlet duct. It's a carbon inlet duct. Currently, we're at 100% repair on all of them. Reason being is we have sacrificial plies we build into them to be able to get the geometry right, as fuel lines have to be at a certain distance from those inlet ducts because hot air going through. But we can learn so much more from actually capturing all this data. As it was stated, we try and shorten the time span, but we only do 1 out of every 10 measurements on each inlet duct or 1 out of every 50. It's getting it to every single one that we want. So we do critical research and development programs on situations like this to be able to better understand what we're seeing to be able to change it inside the process. This is a wind blade. A lot of the wind blade manufacturers today are at a 1 blade a day manufacturing. Now that's quite something. When you can imagine, that blade there is 40 meters. So creating a blade a day, and they go up to 65 meters, and they go bigger than that actually. 1 blade a day is quite something to be able to control your process. Because you're heating these blades up, they're all composite. You're heating the molds. When you heat composites, they change. You have no choice in that matter. When they cool, they don't cool in the same position that they were at. So instead of measuring the molds, you measure every single part. And then you can start predicting what's happening to your mold at that point in time. So it's getting more measurements faster and better. And yeah, with blades, there is an airfoil analysis. It's still technically a wing for an aircraft. It's the same type of process. So one of the projects I worked on and have been working on over a decade is the James Webb Space Telescope. On the right there, we have the Kapton layers, which are 3,000 inches thick and tennis court sized. As you can imagine, very difficult to measure. They came to me and go, we have this material, it's infrared absorbent, extremely reflective. Can't touch it, can't be in the same room as it. How do we measure it? Okay, that's a problem. So we actually used the laser radar system in the high bay. You have to shut down all the ventilation systems so they don't move. They're looking for how it's splayed out. Actually, when it's going up into space, it's going to unfold, unfurl, and it has to unfurl in a certain direction. So it's advanced technologies like this that we have to find solutions for. And going forward, we need to capture all the data. These things have been measured thousands of times, and all of it's aggregated into a custom system at this point in time. What we need to do going forward is to have more things like this. This is a room scanner. We've seen them all week. But the big thing for me is the ability to get these actually more accurate. Faster data capture gives you more accuracy. The longer you take, you have thermal expansion, you have changing in the environment of the room. There's tons of things that change with every second that you're measuring. So if you can set up, say, 5 of these systems, measure within 30 seconds apart, each part you capture is a snapshot of what it was at. So that's actually a Boeing part for a landing gear. So after all these measurements, what do we get? We get a first article inspection report, AS9102, if you're in Form 3. If you're in aerospace, you get a PPAP report if you're in automotive. These reports are generally filled out by hand in an Excel document still. And after you're done with it, generally, it's done. You also get a single part report. These are all great. I love them all, don't get me wrong. But they tell me one thing, that the part's either good or bad. So what do we do with this data? We sign it, we stamp it, and we put it into a big box generally right now. The part's good. That's good, but there's a lot more to it. Well, what did we learn off that single part? What can be improved? There's a lot of things to it. So kind of my call to action for a lot of people is feeding process information back in. You take every single part, learn from it, and go forward. So learning from the byproduct of measurement. By that I mean, what did I learn from each and every part I ever measured going forward? So there's human analytics to it. How was it machined? How was it measured? What was it measured with? What material was machined? And that type of thing. So you get statistical information. From this, you get better business decisions. Reason being is, if I know that this machine I have over here, a Haas machine, machines within 0.005 of an inch each time on titanium, and then I have another Haas machine that hits 0.15 of an inch every time for accuracies, why am I putting a 15 thou part on my 5 thou machine? I should always put on my 15 thou machine. There's things like that that we can learn from measurements if you're doing them constantly. Predictive analysis, it touched on it with the GE blades. You're able to go back, understand, and actually predict when that mold's going to fail. It takes a long time to build a mold, 5 to 6 months. So you're able to see when that mold is going to fail, get the process set up, and then move forward and have a mold in place by the time that mold fails. In aerospace, this is doubly important just due to the fact that right now we generally build another mold just in case, which obviously is very expensive. So being able to say, this mold's gonna fail now, let's go ahead and build it, get it done, and you never lose that step. Larger knowledge base. So we take more measurements, we get a larger knowledge base of not only our parts, our humans, our machines, but in general, just a larger knowledge base of what happens on what type of materials. And then the human analytics, being able to tell my guy that works day shift can get this part done in an hour comparatively to the guy at night shift gets it done in 2 hours, and this guy gets it done with 5 thou tolerance and this guy 10 thou tolerance. It's up to humans a lot of times with how it's measured, especially when you're talking the tightest tolerances that you can find. Something that I'm proposing is a product lifecycle, like a product lifecycle management system. I'm coining a measurement lifecycle management system. Something that ties into a lot of different areas. So the product lifecycle management system is something that you obviously have to tie back into. Being able to always place information for a part in the same area. It's funny, we put our mold or our models in the cloud, we put all of our information in the cloud, and then we put our measurements in the desk drawer. It's really backwards for me. So it would tie into work instruction quality. Being able to say, I know this guy takes a little bit longer, so let's go ahead and structure it so he knows time frame, how long it should take, how to do his job, get it done quicker, faster, easier. You can also tie it into metrology software, the actual measurement software. Have them tied up, throw it into the cloud like we like to do, and have every single piece of information you take go into the cloud for better understanding. If you have measurement plans for metrology software, basically it steps you through, you can actually take and say, this hole has been within 2 microns for at least 100 parts. Let's take that down to measure that hole every 50 parts, because it's not moving. You can also do it to machining software. Machining software, I've been around it for a long time, actually. My uncle's company builds custom robotic machines. And everybody I've ever met that builds robotic machines has always told me, yes, ours hit this tolerance every single time. Well, that's not true, because who's ever doing the machining is picking the paths, the parts, and everything else. So you can actually tell if this guy machines a part to this guy machines a part after you measure it. Because if they're not doing exactly the same every single time, there will be a difference. So if you're using a 3 flute to a 2 flute, you can actually see that in the measurements, especially when you're doing tight measurements, because there'll be a little swarf or chip or chatter going into the actual part itself. So it's just looping the information back into the process to make everything work easier and faster and a better understanding for everything. So after that, you have suppliers. If you can actually centralize a database to where your suppliers, their suppliers, and their suppliers all load into the same centralized database for all this information, you can actually take, say, a part from Turkey that's measured to a part from Everett that's measured, and both measurements are sent to the same interface, which gives you the ability to do a virtual assembly at that point in time. Big problem we have right now is shipping parts that are in tolerance, and this one's in tolerance, but they don't fit together. So when they get to the aircraft, they don't fit. So it's making sure when this measured, you fit them, they're good, then you can ship. It cuts down on time wasting, costs, and everything else for shipping aerospace parts. This also gives you the information of when my parts are being shipped, when the FAI is done, everything else to that fact. It makes it much easier to see pure clairvoyancy of every single thing that's being worked on for your aircraft, your automobile, anything like that. This is the day and age we need to get to be able to take all the measurements, stick them in a database, and actually understand what your business is doing for creating quality parts. And it goes well beyond this even. You can take and stick a database of every machine built, every metrology machine built, and have an understanding of what those machines actually do in the real world. So that basically breaks it down for what I would like to see in this world for the next generation step for quality. A few stories, and then I'm going to leave you just with a quote. If you've ever emailed with me, this is by far my favorite quote by a little known guy, Da Vinci. So, thank you.
Chuck.